Hey guys, first of all, let me start off by saying I'm really sorry that this video took so long to pull together and get out to you. The smoke system and the lighting system were far more complicated than I thought they would be, and by the time I got them figured out, I had run into wing production season, which got into flying season, which got into I don't feel like doing anything season. And yes, in New England, that is a season, sometimes a pretty long one. Okay, so this is part 2 of the wind tunnel build series. And if you have no idea what I'm talking about, or you'd like to refresh your memory and watch episode 1, I'll go ahead and link it up here. Go ahead and watch that, and hopefully this will make more sense to you. In this video, I would like to cover the build of the airfoil support structure, the ongoing saga of the smoke system, and the trials and tribulations of lighting. So without further ado, let's get to it. One more thing we need to talk about before we get on with the build, and that is this wind tunnel's applicability to real-world, full-scale, quantitative results. If you watch the first part of the video, then you know that the test chamber is 12 inches by 12 inches, so it's not a very large test chamber. I'm not going to be able to get anything very big in it. In fact, my smallest model of the Sprite is too big to fit in one piece. So you might be thinking, well, we could just create scale models, put those in, and test those. And yes, we could. That would be pretty simple. But for us to be able to get real-world results, we have to understand that air doesn't scale. Models do. Air doesn't scale. Air doesn't scale. So, in order for us to get any real meaningful results, we would have to do something called Reynolds number matching. And if you're not familiar with what a Reynolds number is, we'll take a quick look at that. Reynolds number is named after a 19th century fluid dynamicist named Osborne Reynolds. Without getting too deep into it, it's essentially a ratio of inertial forces to viscous forces in a fluid. We use it as an indicator of fluid flow regimes. For instance, low numbers indicate a laminar flow, and higher numbers indicate a turbulent flow. For a meaningful correlation, we would have to have our model Reynolds number match our full-scale Reynolds number. Let's take a look at the equation for Reynolds. The Reynolds number is directly proportional to the product of the fluid velocity, in our case air, and the length of the cord of the airfoil. The problem is that as the cord length decreases, the velocity must increase. So, in our case, if we look at a half-scale model at 60 miles per hour, we would need an airspeed of 120 miles an hour. So, for my little wind tunnel, if you do the math, that means we need a 10,000 cubic feet per minute fan. And that is a 10,000 CFM fan. And I can tell you that is definitely outside the budget of this project. There are a few other things that can be done, such as lowering the temperature of the fluid, or air in this case, or increasing the pressure. Both of these go to lowering the kinematic viscosity, which is the number that's in the denominator of the Reynolds number equation. Unfortunately, both of these would require a recirculating wind tunnel. That's a wind tunnel that constantly recirculates its own air, and that is definitely far too big for my basement and far too big for my wallet. So, with that out of the way, let's get on with the build. Let's take a look at the airfoil first. I wanted something to support the test object, or airfoil, that would make it easy to test and allow me to change its angle of attack. And this is what I came up with. I can use a servo mounted on the rear of the door to change the wing's angle. I started by building the rear door panel to fit as tightly as I could. I wanted to make sure it didn't affect the airflow in the test section. I then attached a large panel to keep the inner panel in place. Next, I glued the inner surface of masonite to match the existing tunnel cross-section. And this gives me a nice smooth inner surface. A few screws to secure it. The fit was a bit too tight, but with a little love from a block plane, it's all good. To make the smoke easier to see, I painted the back wall, including the door panel, flat black. The support strut is made out of 3/8 inch aluminum rod that goes through the panel into a bronze bushing. I printed the control horn for the outside and the airfoil support bracket for the inside. I drilled and tapped the side of both so I could add a set screw. This makes it easy to adjust and mount the airfoils. I mounted a standard size servo to the back and attached it to a receiver that is bound to a spare transmitter. This allows me to control the angle of attack of the wing from the front while I'm viewing through the front window. Also, if I wanted to add things like control surfaces and such, I could hook them up to the same receiver and control them from the same transmitter. The smoke system is where things got really complicated. I looked at several different ways to generate smoke or fog and found that the most were either too complicated, too expensive, or potentially toxic. I settled on a Halloween fog machine. These are inexpensive, simple to use, and non-toxic. Remember, this is going in my basement. It's a walkout basement, but still, I don't want any more toxic fumes in my house. The system works by injecting a fogging liquid into a heater. The nozzle on this machine doesn't seem to work well when there's any kind of back pressure or any kind of tight orifice. That didn't sound too good. What I mean is that it needs an air gap to work correctly, so I can't seal it inside the reservoir. I didn't want to seal the whole fog machine inside the reservoir either, because the fogging liquid residue that builds up on the machine, I imagine, wouldn't be very good for the electronics. I went through a few different reservoirs and eventually settled on an 18-gallon tub that I sealed with some weather stripping and duct tape. Real high tech. I wanted to add a pressure tap and pressurize a reservoir from the tunnel itself. Spoiler, this was a complete failure.
You are the dumbest smart person I have ever met in my life.
Also, I added a PWM motor controller to the main fan so I could control the airspeed. I found that visualizing the smoke is best done at low velocities. Okay, so this leads me to the smoke rake. This was the most complicated part of the build so far. It's the part that took the longest and the reason this whole video got pushed off so long. It was extremely frustrating. I'm going to show you two different options that I did. Believe me, there were a lot more than two. The idea of the first rake design was to design a streamlined shape with holes along one side. I figured this would be an area of the rake with lowest pressure and would help pull the smoke into the stream. So I printed this up and set to fitting it into the wind tunnel. I attached it with a flexible hose and added a sealed slider to the top of the wind tunnel so that it could be moved side to side from outside the test section. As you can see, the results were less than stellar. I think that the whole system was too small, especially the holes in the rake. This caused the smoke flow to be too turbulent. I just couldn't get a decent flow. Okay. After a few more failures and a lot more research, I came up with this next design. Spoiler, this one worked. This design consists of a 3/4 inch PVC pipe manifold, a 3D printed attachment, and several pieces of 1/4 inch copper tubing. This gives me much more volume, and the long, smooth pieces of copper tubing help to maintain the laminar flow of the smoke. Again, I started by printing the attachment block that would hold the copper tubing. I drilled holes in the PVC manifold to line up with the holes in the block. I cut lengths of copper tubing that I bought from Home Depot and then bent them to shape with a tubing bender. As you can see, this worked much better. This is the configuration that I'm currently using. Okay, with the smoke system done, now on to the thing that was the next big pain in my ass. Can I say ass? I mean, it's my video, right? Okay, so the next big hurdle, was the lighting. And I went through a lot of different iterations of putting lights inside, outside, combination of both. I even used one of these.
A laser.
This is actually a construction laser, and the reason I chose this is because it uses a flat sheet or line of laser rather than a point. I first tried different LED lights in different locations. This was tough because there was a lot of reflection off the plexiglass. I did some research and found that lasers are sometimes used, so I went and bought a contractor's laser level. This was an expensive purchase and yielded very cool results for images, but because it had to be dark for this to work, it made videoing a challenge. Eventually, I added another plexiglass viewing window to the top of the test section and added a very bright LED work light. I built a black shade for it so that I could keep it from shining on the front window or the rear wall. This did the trick. Okay, now that everything is in place, I'm finally starting to get some good results. So at this point, I'm really happy with the results I'm getting. But I think I want to take this a little bit further. The visualizations are great, and I'm really enjoying seeing the different flow patterns around the different objects. But I think I'd like to start getting some quantitative data out of this. And to that end, I've decided to go ahead and build a 2-axis balance. Basically, this will be a mechanical balance with some digital strain gauges that'll be connected to an Arduino board. And while I'm at it, I'm going to go ahead and get some airspeed data, some temperature data, and some angle of attack data. All of this is going to feed through an Arduino controller, so there'll be some Arduino programming. And then this will all go to a computer interface so that I can record the data and graph it. So that means I'll be developing an interface also to run on the laptop. And with any luck, all of that will be in part 3 of the video, and I promise that it is not going to take me a year to get that video pulled together and out to you guys. So with that, I think that does it, and I will catch you on the next one. By the time I got them figured out, I was running into wing production season. One thing before we go any further into the build, there's one thing about this model wind tunnel. All right, one last thing before we get to the build. There's something I want to clear up about okay, so everything seems to be working, but you should know by now that I'm not going to stop here.